So today we're going to talk about Biot-Savart Law, which is nothing more than the magnetic equivalent of Coulomb's law. The way it works is this. Let's say you have a positive charge, and you throw the positive charge. Hopefully you don't hit the computer monitor. And as the positive charge is flying through the air, which way is it moving?
That way.
That way. So everybody grab your right hand. No, wait. Don't grab your right hand. Hold out your right hand. Put your thumb in the direction that the charge moved. I know, that's just a little hard. Sorry. All right. Then, if the charge was above your hand. No, sorry. The charge is moving that way. If you wanted to know what the magnetic field direction was for a spot that's above the charge, which way would that magnetic field point?
Pointing towards us.
Toward the back of the room. Now rotate your hand around if you can. That might be physically impossible. What way would the field point below the charge? Towards the front of the room. And then in the front of the charge it would point up, and behind the charge it would point down. Good? I should have thrown the ball the other way. Sorry about that. All right, so here's the basic idea. In 3 dimensions, this gets the diagram looks a little complicated because it is. Because look at how many angles we have involved here. All right, we've got the particle. This is the particle. It's moving this way. This is this velocity vector. I tried to draw 2 planes just so you could see like a visual reference. This is an up-down plane, and this is a sideways plane. If I wanted to know the field at a point that was in front of the charge and a little bit above, well, that field direction we could figure out from the right-hand rule would be this way. Agree? Mm-hmm. Now, so that's fine. That's how we get the direction of the field. Oh, what about a point right here that's directly above? Which way would the field point? Same direction. What about a field? What about behind the charge right here along the same plane?
Along the same plane? Or
Yeah, it's this vertical plane I have drawn here.
Same direction.
It would still point in the same direction. It would just be different magnitudes. It'd be different strengths. In fact, it's strongest right here directly above the charge. As you get further out in front, it gets weaker and weaker and weaker. And further behind, it's weaker and weaker and weaker. Sound good? Mm-hmm. All right. And if I would have asked the question, at this point right here on the horizontal plane, which way is the field point? What's the answer?
Down.
It would point down. Good. And then anywhere along this plane, the field would be pointing down. All right? So you use the right-hand rule to figure out the direction of the field from a moving charge. But the tricky part is the strength of the field. Now for Coulomb's law, strength of the field was easy. It was just KQ over R squared was where R was the distance between the charge and the point you're figuring out where the field is. But for a Biot-Savart law, it's a little bit more complicated. Is it over R squared?
Yes.
Sure, because it's a point charge. But remember how yesterday I mentioned that a stationary charge doesn't produce a magnetic field?
Yeah.
So what's that mean?
Needs velocity.
Velocity matters. So there's the velocity in the equation. And of course, if there's no charge, is there any field? No, so charge matters. So charge matters, velocity matters, and here's the weird part. Angle matters as well. And when I say angle, I mean the angle in between the velocity vector and the r vector. Mm-hmm. And it's according to sine theta. So when is sine theta equal to 0?
When it's right in front.
When it's right in front. So if this particle is flying along through the air, what's the field right in front?
0. None.
None. What's the field right behind?
None.
None. There's only field, and the field gets stronger. It's strongest directly above and below. There's no field in front, and there's no field created behind. It's kind of a weird effect. Like, intuitively, you would think that the field would be strongest in front, but it doesn't actually work that way. It's a sine, not a cosine. All right, sound good?
Mm.
All right. All right, so here we go. Just finishing out the equation here. Velocity is the direction of travel. R is the angle between the v vector. Oh, sorry. R is the vector from the charge to the point. All right. Theta is the angle between v and r. B, the magnetic field direction, is perpendicular, right, according to the right-hand rule. Magnetic field strength, B. Do you guys know what it's measured in? Starts with a T. That's your hint. Tesla. Magnetic field's measured in Tesla.
Wait, is it B field because of this law or no?
Why do you call it B field? That's a good question. The best answer I can give you is because at one point somebody sat down and just started assigning letters. They started with A, B, C, D, E, F, G, H.
Wait, what does M stand for?
I don't know if... yeah, it might be mass, yeah. Yeah.
Big M, little m.
I mean, I think that's the story. I'd have to look that up. But I really do think it was random letter assignments because they needed letters for everything that they were talking about. And magnetic field was just what the next in the list, just randomly. I mean, E field was electric field, F was force, you know, but some of them just make absolutely no sense. P was momentum. I have no idea where that came from.
It could be like a Greek or Latin rule.
Yeah, I don't know, but I like the randomly generated list theory the best. All right, so here we go. Yeah, here we go. Remember how K was equal to what was K equal to? 1 over 4 pi epsilon naught, right?
Mm-hmm.
So mu naught is the magnetic, whereas K was the electrical permittivity of free space or electrical permittivity of a vacuum. Remember how K had to do with capacitors? It also had to do with Coulomb's law. Well, or sorry, epsilon naught rather. Well, mu naught is the magnetic version of epsilon naught. All right? And so the equation for Biot-Savart, instead of being 1 over 4 pi epsilon naught, it's mu naught over 4 pi.
And what is the magnetic?
Yeah, so mu naught is the magnetic permeability of a vacuum. It's like epsilon naught just for magnetism, not electricity. And here's a weird thing. Mu naught actually, when they measured mu naught, they found it to be really close to 4 pi. And so guess what they called mu naught? 4 pi. 4 pi times 10 to the negative 7th, but still 4 pi. So when you end up using the Biot-Savart law, what happens to the 4 pi?
It just cancels.
It just goes away. So you end up with 4 pi times 10 to the 7th on the top. Sorry, 4 pi times 10 to the 7th up here, divided by 4 pi, and it makes your numbers work really nicely.
10 to the negative 7th, right?
Yeah, 10 to the negative 7th. Got it? So, yeah. Is that a coincidence? Yup. One of astronomical proportions. All right. So, yeah, we use 4 pi as mu naught. 4 pi times 10 to the negative 7th as mu naught. All right. Okay, direction conventions, you know what these symbols mean, right? Up, down, left, right, into the page, out of the page. You had to do that on your homework yesterday. And it's got an explanation. All right, so here is the actual mathy stuff. Let's say you have a negative charged particle moving to the right at 2 meters per second. And I want to know the magnetic field at these 3 points. Due to that, what's the magnetic field at 1 going to be? Point 1. Hint, the electron is moving away from that point. Directly away.
Oh, 0.
It's going to be 0 magnetic field, right? Because it's a sine of 180 degrees, which is 0. And then the other 2 points, let's see, this one, what angle do we use? Yeah, 135 or 45, right? So sine of 135, and then this one, what angle do we use?
90.
90 degrees. Good.
I like the one that's straight up better.
Yeah.
That's one.
Yes. Agree. All right. And then also, yeah, and don't forget, because this is a diagonal, you got to use Pythagorean theorem to figure out the distance too. Right? So you got to do, not only is it a 135 degree angle, but the distance is funky. The distance in this case is square root of 2. Square root of 2 squared, which is 2, but it's not always that nice. All right, so next one, moving on. Cross products. Raise your hand if you've done cross products in math class. Everybody raise your hand. Because you all did it, because you're all in BC, right? Or beyond? Yep.
We did them in algebra.
Did you do it in Algebra 2 when you did determinants?
Yeah.
Why didn't you do it in BC?
In BC, we didn't.
We
both
multiplied.
times we did.
That's weird. But you did dot products in BC.
No.
We did that in it's all
We.
No,
I
dot
don't
products is
remember.
it's like a pre-calc topic.
Yeah.
I was tutoring somebody in BC, and it was like they're doing cross or dot products right now. Okay.
What? Are you sure
Because they're doing it with they're doing a big unit on vectors, and they're doing path like arc lengths using parametric equations, and then they did dot products with that. So, which is kind of a multivariable topic anyway, but it's a vector topic. Whatever, it's just a vector topic. So anyway, here we go.
I don't remember.
Cross product. There are 2 ways to calculate a cross product, just like there are 2 ways to calculate a dot product. You guys remember what the 2 ways to do the dot product were? It was AB cos theta. That was way number 1. And the other way was to say AI times BI plus AJ times BJ, right?
Yeah.
Okay, and then add those up and you get a number. Cross product is a way to multiply 2 vectors and get another vector. Whereas dot product gives you a scalar answer, cross product gives you a vector answer. Well, again, there's 2 ways to calculate it. What's way number 1?
Do the determinant of the.
I was going to say AB sine theta,
Oh.
right? Because dot product was AB cosine theta.
Sure.
So cross product's AB sine theta. But instead of doing this nice, easy AI BI plus AJ BJ, you have to do a determinant. Right. And what you do is it's a 3-dimensional thing as a cross product. It's I hat, J hat, K hat. So if you don't remember how to do that determinant, no worries, it's pretty easy. You can look it up. You just cover up 1, cover up I hat, multiply CJ DK minus CK DJ. Remember all that stuff?
Add all the
Cross
diagonal
in.
downs, subtract
Right.
all the diagonal ups.
Right. Now, you probably aren't going to have to do that on the AP test. Probably. I'm trying to think if it's ever been asked. It might have been asked once in like the 1970s at some point. They were big on this kind of stuff in the 70s in physics. But I don't think you're going to be asked that. But it's a math thing you should know. You learned it in Algebra 2. Or in trig or pre-calc or whenever you did that. But you do need to know how to use the true full version of the right-hand rule. All right, so everybody pull out your right hand.
Oh, we did this in multivariable too.
All right, right hand. So let's say we want to calculate the the cross product of vector C and vector D. All right, take your right hand. Let's say C points this way, D points that way. So C points kind of down like this. We move our our lower fingers in the direction of D, so it's C then D, and then our thumb points in the direction of the cross product of C and D. So what do you notice about the direction your thumb points versus the direction of these two fingers?
Perpendicular to both.
Always perpendicular to both. So C and D define a plane, and the cross product is the normal to that plane. Good?
Yeah.
All right. All right, so yes, you are going to have to use this all over the place in magnetism. I love giving the magnetism tests. You know why? Because you all look like idiots. And it's one of my favorite things to see everybody doing this with their hands during the test. And they're like trying to get, and you look really stupid and it's funny.
The AP test, the grade looks that we get.
Yeah.
Yeah, the
Awesome.
AP graders are like,
Like, what
hey, are they doing magical science?
Oh, did you? God, did you?
They're cursing us.
It looks like you're sign languaging.
Yeah.
Yes, this is my sign language. Yo.
I gotta focus on my test.
All right. So the version of the Biot-Savart Law on the previous pages is useful for only a single point charge. But what if you have an entire wire full of point charges? Ooh, entire wire full of point charges. That sounds shockingly like a wire with current in it, right?
Serpent.
Shockingly. Thank you, Sean, for pointing that out. Yeah. So the Biot-Savart law is actually how you would derive the magnetic field from a loop, from a wire. All right. So what you do is you say, let's say I have a wire of length L. How many charges are in it?
Infinite.
Infinity, right?
Yeah.
Yes. But every single one of those charges is contributing to the magnetic field around it, right?
Yeah.
So what you can do is you can integrate over the length of that wire and figure out what the magnetic field is around the wire.
Integral of charge.
It's the integral from one end of the wire to the other end of the wire, right? And so, which gives us the version of the Biot-Savart law that's actually on the orange sheet. They don't give you QV sine theta over r squared. What they give you is I dl cross r over r squared. We're actually over r cubed. That's a typo. Why is it over r cubed? Oh no, sorry. This is r hat. Yeah. What do you guys know how big r hat is? Do you guys know what r hat is? Do you know what a little hat means over a vector? Pointy thing?
That's a.
It's a start with a u. It's a unit vector, right? How big's a unit vector?
1.
1, which means it basically says cross the dl vector with the r hat vector to get the direction of the magnetic field, then divide by r squared to get the size of the magnetic field. All right, it's a really, really confusing way of writing. It's a compact way of writing that do all the stuff, figure out the amount of it, and then use the right-hand rule to figure out the direction. All right. All right, so here we go. And the derivation's in here. You can look it up, read it at your leisure. All right, so here's the version that is on the AP exam. They do IDL cross R over R cubed. Why is it over R cubed here? Why is it over R cubed? I mean, isn't it supposed to be over R squared?
No, because now the r is a vector rather than a unit.
We want it to be over R squared, right? But if you put an R on top, you got to put another R on bottom to make it R squared. Does that make sense?
Yeah.
So one of the R's cancels, so it's over R squared. But this is the version that's on the AP exam. So if you see that, don't freak out, something over R cubed. It's really over R squared. All right. Okay, here we go. Example using the AP exam version of the Biot-Savart for a point charge. Okay, so this is where it gets goofy. We like QVB sine theta, right? But we don't get that. We get this weird IDL cross R over R cubed thing. So what you do is you just rewrite it. So they're going to give you this one. You're going to rewrite it this way. And this rewritten, to get the magnitude, it's QV R sine theta over R cubed, or QV sine theta over R squared. Good? That's the magnitude, and the direction is given by the right-hand rule. So like we did at the very beginning of class today. So in the end, this is what you're going to be using for the magnitude, and this is what you're going to be using for the direction. But what's written on the page looks like this. Got it? All right. That wasn't confusing at all. Yes? DL, a little length of a piece of wire.
So DL over DT.
DL over DT.
That's what it shows.
Oh, right. IDL. I is DQ over DT, right? So DQ over DT times DL. But DL over DT is velocity, right?
Oh, I was thinking that was
Rate.
I got so confused.
Yeah, velocity. So dq times v is charge times velocity. Charge times the speed of the charge. All right, so here we go. And that's it. So your homework today is, I believe, line charges, or is it point charges? I'm not sure which. It might be moving point charges, and then we'll do line charges when we get back. So let's take a look.